Hi class, so we are continuing our discussion regarding design of shallow foundations, no? So before you watch this video, you have to make sure na you already watched, no, my previous video, no, and somewhat familiarize yourselves with what I've discussed before, no. So ngayon, no, uh, we are going to check now, no, if our designed footing, no, designed na uh, if our concrete footing, no, somewhat adequate, no, somewhat strong, no, against various failures, no, that may occur due to, of course, the load from the structure, from the column, no, or from the wall, and the bearing capacity, no, and the bearing failure, no, from the soil, no. So uh, let's start, no? Okay. So continuing from what we've started from the first problem, no? Look at the figure on the left, no? So you have here a footing, no, with already the dimension na nahanapan natin, no? So yung nasa top na figure on the left, no, is the section, no? Ito yung itsura ng section niya. And then yung nasa ilalim na figure is yung plan view, meaning from the top, no? Kapag tumingin ka sa taas, if you look from the top, this is what you're going to see, no? So you have your 500 millimeter by 500 millimeter column there, no? And you know that we are designing base, or I'll rephrase that, no? We are going to assume na there's a factored load acting on the column, no, which will be transferred on the footing, no. So from the footing, no, it will act on the soil, no, and at the same time the soil will act back also, no. So yung lipat nating yung nilipat nating load from column to the footing, no, is your bearing capacity, your assumed bearing capacity denoted by QU, no? So yung bearing capacity na galing sa soil papunta sa footing, no? Is the one that will cause failure on your soil, no? When it comes to one-way shear, no? So let's look at the code, no? So let's look at the code, no? On ano ba yung sinasabi, what does the NSCP says about shear failure, no? So let me transfer our window to my NSCP file, no? Okay, so here's the one-way shear, no? So you know na ang one-way shear is also called as the beam shear. So therefore, we are going to analyze, no, our footing like it is a beam, no. So we look at section 409, no. So from section 409.4.3, it is written that sections between the face of the support and a critical section located D from the face of the support for non-pre-stressed beams and H/2 from the face of the support for pre-stressed beams, no, shall be permitted to be designed for view at the critical section if A through C are satisfied. So number 1, letter A, support reaction in direction of the applied shear introduces compression into the end region of the beam. No, so ang sabi there is a support reaction daw, no, in the direction of the applied shear. No, so yun, letter B, loads are applied at or near the top surface of the beam. No, so and third condition, no concentrated load occurs between the face of the support and the critical section. No, so here are the conditions, no, written. No, so ano ba yung ibig sabihin nun? No, kapag ano yung ibig sabihin ng code natin when it comes to ano ibig sabihin ng code, no? By those conditions, no? Okay, so let's go back to our figure. Okay? Going back to our figure. Okay? No? So from our figure, ang sabi, no, the critical section daw will be, no, at the distance d, no, from the support. No, so we are going to measure a distance d, no, from your support, which is also your column, no, and it is applicable, no, provided written from section 409 of your NSCP, no, that ano ba yung mga condition ulit na sinabi, no? Ang sabi, support reaction in direction of the applied shear, no, introduces compression into the end region of the beam, no? So uh, there is a uh, there is a support reaction, no, so on the end region of the beam, no, so if you apply yung support nyo, no, the support is from the face of your column, no, kasi nga yan yung the support will be from the face of your column, no, and uh, it introduces compression on the end region of the beam, no, so malamang sa malamang meron siyang reaction here, no? Ang pag in-isolate natin yung section na to. Letter B, loads are applied at or near the top surface of the beam, no? So loads are applied at or near the top surface of the beam, no? So meron din tayong load, no, on the top surface, no, of the beam, no? So meron tayong load dito. And then letter C, no concentrated load occurs at between the face of the support and the critical section. So wala naman tayong any load, no, except for the distributed load, no. So we can say that this is your critical section. Pero ano ba ibig sabihin din ng NSCP? Bakit meron pa tayong distance D from the support, no? Pwede naman nating sabihin the face of the support na lang, no? Kasi nga dito maximum yung shear natin, eh, no? Dito pinakamataas yung shear natin pag pinutol natin 'to, no? It's because, no, the failure, no? Pag nag-fail siya, no, when your footing here or sabihin natin na beam ito experiences shear failure, ang failure niya usually diagonal, no? Starting from the face of your column, no, pababa siya doon sa sinasabing critical section, no? So diagonal ang itsura ng failure niya, no? So therefore, we cut that out, no? So therefore, we cut this, no? We cut this section, no, from magme-measure tayo ng distance D, no? Ang D pala dito, ang sinasabing D dito, yun din yung effective depth natin, no? Meaning the distance from the top portion of your footing up to your reinforced, no? So pwede nating ito na yung itsura niya, no? So ito yung QU mo, no? This is your QU, and it's acting, no, uniformly on the section, no? Pero, no, kapag ka nakaharap sa iyo yung footing, no? So ito yung itsura niya, no? Parang 2D lang siya na uniformly distributed load, no? So paano natin gagawin 'yon, no? Ang VU natin, no, shall be equal to the QU. Yung QU natin kanina, remember, is equal to 384.305 kilopascal multiplied by 2.9, no? So yung 2.9 natin, that is one side, the other, that is the dimension of the beam, the footing rather, no? Dahil square naman to, no, we can just do one computation, no? Kasi both sides naman siya, no? Multiplied by yung distance na to, no? So oo nga pala, no? Pag nag-analyze tayo na inassume natin na it's a beam, no? Pwedeng gamitin natin yung kaliwa, kaso meron pa, tandaan nyo, meron tayo concentrated load dun sa column. So medyo mahihirapan tayo, no? Para mapadali na lang, no? Gagamitin natin yung kanan. Ito yun, no? Look at the figure on the right, no? So that's how it looks like. Multiplied 384.305 multiplied by 290. 2.9 is this one. So ang magiging itsura niya, mukha na siyang uniformly distributed load na two-dimensional, no? So we are also going to multiply this by this distance. Itong distance na to, no? Let's go back, no? Ito yung from the right side of beam up to the critical section, no? So paano ko na-solve 'yan, no? So paano natin na-solve 'yan, no? That is ang dimension natin is equal to 2.9, no? 2.9 minus the column dimension, which is equal to 0.5. We divide it by 2, makukuha natin to. Pero binawasan pa natin ng D. So 2.9 minus 0.5 over 2 minus D. No? So tandaan, no, the D, ang D na to is in meter. Pero kailangan nasa millimeter siya, no? So either I just divide it by 1,000, no? Oo nga pala, no? You remember, medyo para hindi tayo maligaw, no? There are two ways in order to check if our beam or our footing is adequate against one-way shear. So una, we compare, no, yung kinompute nating effective depth, no? Gagamitin natin yung kinompute nating effective depth at saka i-check natin yung kung pasok ba yung load natin doon sa code, no? So una, we compare it, no? Pero and the next method will be we compute the minimum depth, no? So ang ginawa ko dito, no, inassume ko muna na I assume first na yung D natin, no, ginamit ko yung na-solve nating effective depth kanina, which is equal to 150 mm. So nung ginamit ko yun, no, so minus 150 over 1,000 kasi in meters lahat ito. And our VU is equal to 1,170.209 in kilonewton. No? So tandaan, kilopascal is equal to kilonewton per meter square. This is in meter, no? This is also in meter. No? Okay? So it is written, no? Location of critical support for one-way shear. No? So saan natin i-compare tong VU na to? Itong VU na to, ito yung actual na shear na, yung design shear natin. Not necessarily nangyayari. Pero of course we know na kapag na-reach na ng pag na-reach na ng load natin, no? Yung pag na-reach na ng foundation natin itong load na to, meaning to say it's bound for failure already. Pero who knows, no? What should we do is we compare it into we compare it on using our code, no? So this is from section 422.5.12, no? So VU, no, is equal to your fee, no? So fee natin, no, fee multiplied by VC, no, plus this is your VS, no? So ang VC natin dito is the shear that can be carried by your concrete, no? So yung VS natin is your shear reinforcement, no? So we all know na hindi natin pwedeng lagyan ng stirrups ang footing, so therefore your concrete should be strong enough to carry one-way shear. Okay? No? So ang magiging ano ang mga formula na to, no? Tong fee natin at saka yung VC, no? So from VC, ang formula natin for VC, no, written from the code, no, from section 422.5.5.1, no, VC is equal to 1/6. This is capital V, no. The small v is different, no. So 1/6 multiplied by lambda square root of FC prime, no, BW, the base, multiplied by the depth, the effective depth. No? So this is an empirical formula in Newton, no? So you have to remember na kung Newton yung formula natin Newton yung kalalabasan na formula na unit dito, no? So you have to remember na this F prime of C is in megapascal or Newton per millimeter squared, no? Yung BW natin is in millimeter, ang depth natin is in millimeter, no? So I don't want you to commit grave mistake, no, especially in unit conversion, no. So what is the formula for your lambda, no? So your lambda, no, dahil didn't tell anything about being a lightweight concrete, no, written from table 419.2.4.2, no, your lambda is equal to 1. So from your codes, you might try to look at that as well, no? So you want me to show, let me show you that, no? So let me show all that specifically, no? Okay? Okay. Yan. So ito yung code natin, no? So let's proceed with section 422, no? So this is your Vn is equal to Vc plus Vs, no? So we don't need your Vs kasi nga we don't have to put stirrups, so therefore Vn is only equal to V sub C. So Vu is equal to Phi multiplied by V sub C, no? Okay, ang formula natin for V sub C, no, is equal to this one, no? So ginamit ko yung 1/6 doon, no? But you can also use 0.17, no, if that is written on your code. Pero that will just be the same, no? Kasi I'm still using NSCP 2015, but I'm using the second printout, no? My soft copy is the first printed edition of the NSCP, no? Okay, no? So this is your formula for V sub C, no? And your VU is equal to phi. Yung phi natin dito is your reduction factor, no? So let me show you what is reduction factor, no? So it's written here, no? So this table provides reduction factor, and we are designing for shear, so therefore the phi that we're going to use here is 0.75, no? So yung lambda naman written from lambda naman natin written from section 419, section 419, this one. This is from section 419, no? Okay. So we are assuming that it is a normal weight concrete from table 419.2.4.2, no? So our lambda is equal to 1.00. Okay? No, so you might I assume that you are already familiar with the formula from the code. No? So ang lumabas natin, no, when we decided to compare, no, your VU, yung computed VU natin, which is equal to 1170.209, no, here, and your phi VC, no, phi is equal to 0.75 multiplied by 16 times 1 square root of 27.5 multiplied by 2,900. 2,900 is the big step here, no, this one. Okay, and then multiplied by our computed depth equal to 150. No, so our VC is equal to 285,144.9056 Newton. No, so pagka ang VU natin pag in kilonewton, pag minultiply natin ng 1,000, it is 1 million plus. So therefore, we know na it fails. No, okay. So, how are we going to redesign your footing? No? So, we redesign depth, no? Okay, by doing our second method. No? So, this is the first method. No? Let me show you the second method of computing, of redesigning the depth of your footing, no? Or checking the adequacy of your footing against one-way shear or beam shear. Okay. So this is the second method, no, in checking the adequacy of your one-way shear, no, checking the adequacy of your footing against one-way shear, no. So una, i-compare natin yung VU natin sa phi multiplied by VC. Pero ang gagawin natin dito, no, gagamitin na natin yung mismong VU to determine the minimum depth. No, so ito na yung method na ginamit ko on other means of failure for footings. No, so let's determine, no, the minimum effective depth of your footing, no, in order for it to withstand one-way shear. No, so ito yung VU natin, 384.305, no, multiplied by 1 megapascal over 1,000 kilopascal. Kilopascal na to, kinonvert ko siya into megapascal multiplied by 2,900 kasi you should know na ang depth natin should be in millimeters. No? So multiplied by 2,900 multiplied by 2,900 minus 500 over 2 minus the depth. No? So ito yung VU natin kanina, which is equal to V, which is 0.75 multiplied by 1/6 times 1 lambda square root of f prime of c 27.5 times 2,900 multiplied by d. No, so we are able to solve for value of d here, no, just using shift solve or uh, any other means, no, from your algebra, no. Okay, no, so yung d minimum natin in order for your footing to withstand one-way shear is equal to 443.51, no, 5096 millimeter, no. So Ito na ba yung gagamitin nating bagong effective depth, no? So let's check, no? So on the later videos or on the later parts, no, gagamitin ay ano, i-check muna natin, no, if this is already the minimum depth, no? Baka kasi syempre, no, may lumabas pa na mas mataas na required, no? Kaya let's leave this to be first. Okay? No? So let's move on to our next problem, no? Concerning also one-way shear. For sample problem number 2, no, let's consider this part of our notes, no, this figure, no. So we all know na on sample problem number 2, they have two different dimensions kasi nga it is a rectangular footing, no, you know. So what are we going to do now is to uh, analyze it individually, no, along the longer span, no, so and along the shorter span. They both have the same concept, pero ang magkaiba lang is the dimension, no. So along the longer span, no, so let's assume natin na ito yung 4.8 meter natin. And then, ang critical section natin is this one, no? Parang beam siya. And we compute this distance, itong distansya natin, no? So, we compute your x as 4.8 minus 0.6 over 2, no? And this is equal to 2.10, no? Pero ibabawas natin yung d min. No? So therefore your x now is equal to 2.10 minus d minimum. No? Pero syempre, we want our d, no? Yung d minimum natin na i-solve natin mamaya to be in millimeters. So we just divide it by 1,000. No? It is written here naman. No? Okay? No? So nga pala, no, I decided to use method 2 na lang, no, instead of method 1 para hindi tayo paulit-ulit, no. So method 2 na tayo wherein we just equate yung VU at saka VBC natin, no. I-equate natin silang dalawa to determine the minimum depth. And ang ang depth na inassume natin sa simula pa lang, no, is above the D minimum, no? Ibig sabihin, pasok yung value natin ng D. Pero kung hindi, yung D minimum na ang gagamitin natin. So dito, yung VU natin is equal to 271.88, no? This is in kilopascal again, multiplied by 3.20 multiplied by 2.10, no, minus the minimum, no, over 1,000. Huwag kakalimutan yung over 1,000 kasi yung d minimum natin should be in millimeters. Okay? Next, yung VC natin from the formula again, from the code, 1/6 lambda square root of f prime of c BWD. No, so yung BW natin, no, nakaharap tayo dito sa 4.9. So therefore, yung dimension na hindi natin nakikita is equal to 3.2, yung the other dimension. So therefore, is equal to 1.6, 1 over 6 multiplied by 1, no? Lambda natin is also equal to 1, no? From the formula, square root of f prime of c, 28, and times 3,200 times d min. No, so equate them with each other. No, 271.88, 3.20, 2.10 minus d min over 1,000 equal, no? Multiplied by 1,000 dito kasi ang nakuha natin ditong VU is in kilonewton, no? Pero newton to, yung VU natin dito should be in newton dahil ang VC natin is also equal into Newton, no? So therefore, this is equal to 0.75 multiplied by 1/6 times 1 square root of 28, 3,200 D minimum. No? So equate them with each other. We have D min is equal to 611.74. No? So let me remind you again of the units. No? Newton, ay ano, this is in Newton, yung VU natin, Newton dapat. Dahil yung VC natin is also in Newton. Yung 0.75 from the code dahil shear ang ina-analyze natin. Okay. No? So, next part. Let's analyze the other side, yung along short span, no? So it's just the same, no? Pero ang kinaiba lang, no, nakaharap na tayo sa 3.2 meters, no? So yung hindi natin nakikitang dimension is the 4.8 na. Okay? So VU natin is equal to 271.88 multiplied by 4.8 multiplied by 1.3 minus D minimum over 1,000. No? So, bisin natin 1/6 lambda square root of f prime of c bw d. No? So, 271.88, this one. VU is equal to V. No? Multiply pa natin ng 1,000 para maging Newton. Is equal to V, 0.75 VC. We are able to solve for D, no? Which is equal to 307.70. Okay, so for sample problem number 3, no, this is a wall footing, no. So what we did is we analyze a 1 meter strip, no, just like when we design one-way slabs from your RCD, no. So ganito ang itsura niya, okay. Same pa rin, no? The critical section is at a distance D from the face of your wall, no? So pag nag-top view tayo, this is how will it look like, no? So x minus D minimum. And the value for your x is equal to the 0.8, no? Yung dimension of our wall footing minus our wall, which is equal to 0.25 divided by 2, no? And then equal to 0.275, no? Then we reduce, no? Then we babawasan pa natin siya ng D, no? So parang nag-drawing, parang ang itsura niya, ito yung parang this one is a beam, no? Okay, it looks like a beam here. Okay, no? So VU now is equal to 160 multiplied by 1, no? 1 meter multiplied by 0.275 minus D minimum over 1,000. No, this is in kilopascal din, no? VC is equal to, no, 1/6 multiplied by lambda square root of f prime of c bwd, no? We input all the values also and then equate them all together, no? So we equate them all together. We equate them all together. 160 times 1 times 275.275 minus D minimum over 1,000. Dahil this is in kilopascal, meter, no? We multiply this by 1,000, no? Para maging megapascal siya, no? Or para maging Newton, no? And then 1 is equal to 1/6 multiplied by 1 square root of 21 times 1,000 D, no? Multiplied by 0.75, no? So ito ay Newton. Yung VU natin dito is in Newton, no? VC is in Newton, no? And then we multiply it by 0.75 also, no? Ito yung phi natin, 0.75, no? They are all just the same. We are analyzing shear here, kaya 0.75 yung value of phi from the code. no? Ang D minimum natin, when we equate them all together, it's equal to 60.04 millimeter. Pero sabi na ang ah, minimum na effective depth natin is equal to 150 millimeter, no? So therefore, yung inassume natin kanina for in the case of wall footing, no, is correct, no? It's usable, no? We can use 250 millimeter thickness, no? O nga pala, bakit I already concluded 250 millimeter as its thickness, no? Kasi we don't need to analyze, no? We don't need to check the adequacy of your wall footing against two-way shear. Kasi it's a long wall, no? And punching shear will not occur, no, on wall footings, no? Okay. So uh, that's all for one-way shear. Okay, and that ends our video, no, for one-way shear, no. So expect that on the next video we're going to check naman yung two-way shear. Okay, no? So like what I said again, no, two-way shear is only specific for footings that support columns, no? So therefore, wall footing will be excluded from the narrative kasi of course it's a long wall, no? It's not acted on by a concentrated load, no? So again, no, if you have any questions, don't forget to like and subscribe, no, to this channel, no. Check your Blackboard, no, and always and I'm leaving yun naman my social media account and my email, no. Okay, so see you next video.